Welcome back to Power Forge and Workshop. Today we are going to calibrate this wonderful Pioneer probe, the OP-510, the OP-510. All right, and I'm ready. A few days ago, maybe it was last week, we calibrated the tool setter. I want to get this probe recalibrated so I can start making some chips again. So I've got some stuff. Let me set this down. Of course, I've got my manual, so I can run all of the calibration routines. It's all laid out in here fairly well. There are some confusing moments, but I think together we can get through it. I've got a ring gauge, certified ring gauge with an exact inside diameter. We'll be using that in a couple of the tests. And then I've got my Mitutoyo dial indicator so we can check the run out. So without further ado, let's get to it. There are 4 calibration routines outlined in the manual. These routines calibrate the eccentricity, the radius, the length, and the vector radius. Before calibrating the probe, it's a good idea to verify the run out with the probe and the spindle. Additionally, after replacing the stylus, the run out should be verified and adjusted as needed. According to the manual, to achieve the highest accuracy, the probe should have between 0.002 and 0.003 millimeters of runout. That's about 1/10,000th of an inch, 0.0001. The manual also states that the OP-510 probe is adjusted at the factory to that specification. The stock stylus has a 6 millimeter ruby tip with a 40+ millimeter ceramic shank. As with most probes, the stylus is the single point of failure and will break easily if you're not paying attention. If the stylus collides with the part or vise, especially when traveling in Z, it can easily be sheared in half. This is a common occurrence, and new probe tips can be purchased. The model number is listed in the manual. Note the position of the magnetic base and dial indicator. In this configuration, we can measure the run out of the ruby as the spindle is slowly rotated. The current run out of my probe is about 0.001 inches or 0.0254 millimeters. That is nowhere near the accuracy called out in the book and will need to be adjusted. To adjust the run out, we need to adjust 3 screws. These screws not only allow us to adjust the run out, but they also mount the probe to the BT30 shank. This is what we're working with. As you can see here, there's a circular dovetail that captures the screws. As the screws are tightened, the run out of the probe is adjusted, and simultaneously the probe's body is drawn towards the shank. This is a delicate and most times time-consuming process. With 3 screws, you only have 120 degrees of adjustment per screw point. It's best not to overly loosen the screws as the weight of the probe will fight against you. With a bit of practice, I suppose it can be done, but it takes expertise and patience. After working on it for about 20 minutes, I now have it dialed into a bit more than 1/10,000th of an inch, about 0.0002 to 0.0003 inches. Unfortunately, this does not meet the 0.003 millimeters specification. Currently, the run out is approximately 0.005 to 0.007 millimeters. If I can't further improve the run out, I can expect less accuracy and worsen the repeatability. However, there will always be some irregularities with a probe's setup and physical characteristics. I have to assume that part of the point of the calibration routines is to compensate and adjust for these irregularities. The first calibration called out in the manual is eccentricity. As you can see here, the manual suggests calibrating one of 2 ways. The first, boring a hole, measuring that hole, finding its center, etc. Or the second method, using a precision ring gauge. I purchased a ring gauge on eBay, so I'm going to use the second method. To proceed, we need to fix the ring gauge on the table of the mill and find its center. Now there are a few ways to find the center of a bore. One of the easiest is to use a coaxial indicator. Conversely, one of the cheapest, yet still accurate ways is to use a dial test indicator. The first step is to install the dial test indicator in the spindle. I'm using a round bar and clamp that came with my indicator. I installed the bar in an ER16 collet and put it in the spindle. This method may seem crude, but it works perfectly well. First, with the indicator above the ring gauge, rotate the spindle by hand and roughly adjust the dial indicator and the spindle by eye until they are centered above the ring gauge. Next, lower the indicator inside the ring gauge. Using this method, you will need to find 0 in 3 quadrants, left and right of the ring gauge on the x-axis and the front of the ring gauge on the y-axis. First, rotate the spindle, alternating the position of the indicator between the left and right sides of the gauge. As you do this, adjust and find the 0 position in X. Next, rotate the spindle to the front quadrant and adjust in Y until the indicator reads 0. Readjust as needed until the indicator reads 0 in all 3 positions. Now as you sweep the indicator around the ring gauge, it should read 0 throughout. The spindle is now aligned with the center of the ring gauge and we can proceed to the first calibration. Raise the spindle as needed and install the probe. Be sure not to move the table in X or Y or we will be back where we started. Lower the probe along the Z-axis until it passes below the top of the ring gauge, as shown in the manual in section 5.1. Now that we are ready to run the calibration, let's take a closer look at the output and example sections. As noted in the output section, the eccentricity is saved in the R206 and R207 variables in X and Y respectively. Optionally, you can also calibrate the radius variables R208 and R209 by changing one of the values in the program. Let's now look at that example program. This program should be saved in the Program Manager section in your Siemens controller if you ordered the probe when you purchased the mill. If it's missing, or you purchased the probe after the fact, you can use this example to write your own calibration routine using the controller. D1 activates the length compensation function. L9008 resets our variables, and L9023 starts the program. In the example, R4 equals 60 is the diameter of their ring gauge. You will need to input the exact diameter of your gauge. R0 equals 1 will calibrate the eccentricity of the probe. R0 equals 2 will calibrate the radius, and R0 equals 3 will calibrate the eccentricity and the radius together. L9026 starts the eccentricity calibration, and L9024 shuts down the probe. M30 ends the program. To run the calibration program, shut the door, select the soft key next to the execute, and hit cycle start. The Ruby will contact and probe the ring gauge in the X and Y quadrants several times, and the variables for the eccentricity and the radius will be saved in R206 through R209 respectively. Before we calibrate the length of the probe, let's first discuss calibrating the vector radius. Calibrating the vector radius of the probe is similar to calibrating the eccentricity and radius in that the probe must also be centered inside a ring gauge. The purpose of calibrating a vector radius is to enable program L9016. L9016 measures the center coordinates and diameter of a circle using 3 points. This function is available with the enhanced software package. The vector radius calibration sets the radius variables R208 and R209 in directions X and Y, and the radius in 30, 60, 120, 150, 210, 240, 300, and 330 degrees. The example shown here has an additional element that the eccentricity calibration omitted. L9025, which starts the probe with protection. If I understand the example program correctly, it looks like the probe is centered 10 millimeters above the ring gauge as shown on line 4. R1 equals 0, R2 equals 0 represents X0 and Y0, and R9 is extra moving distance. Then the probe moves down 10 millimeters as shown on line 6 with R3 equals -10. I think it's safe to say that we can eliminate locating the probe with protection from the program, provided we position the probe inside the ring gauge as we did before. After L9023 starts the program can follow up with R4 equals the diameter of our ring gauge, and then L9028 to calibrate the vector radius. L9024 shuts down the probe, and M30 ends the program. Now let's talk about calibrating the length of the probe, which I think can be tricky. Following the manual in section 5.3, it asks us to input the approximate length of the probe. You can do this by selecting the offset button and inputting your length variable next to the tool number assigned to your probe. My probe is assigned to tool 12, edge 1, so I would put the approximate length in that position. The manual uses tool number 1, which is perfectly fine. I was taught to assign the probe to the largest tool number, which is now my preference. For me, tools 1 through 11 are for milling, drilling, etc., and tool 12 is for inspection tools, like the probe and my master tool. As we did with the previous calibration, let's take a peek at the manual. You can see in the graph section that the stylus seems to be positioned at a safe distance in Z of 20 millimeters, directly above the gauge block, which has a height of ZZ. The calibrations with the ring gauge run fine as printed. However, whenever I run the length calibration as stated in the manual, it throws an error and doesn't work. Here I'm running the routine above the ring gauge, which is 38 millimeters tall. Let's see what happens. This is probably a user error on my part. Perhaps I'm missing some crucial information to understand how to run this calibration. I have found a couple of hacks to calibrate the length of the probe, although I don't think they are as accurate as a third technique that I'll go over last. One way to get the routine to run and not get an error is to set G500 in Z to 0, and then change the R3 variable in the program to -10. As you can see, it seems to run just fine and spits out an approximate tool length on the tool length offset screen. This method is very easy. Just remember to zero out your G500 after you are done so it doesn't interfere with other programs you might be running. For example, if my WCS is set in G500, I get an error when I run my spindle warm-up routine. A second way to get the calibration to work is to use a bit of code that tells the program to move down in Z relative to the machine's work coordinate system. If we look at this program, you can see that I have replaced R3 equals -10 with R3 equals $AA_IWZ -10. This directs the spindle to go down 10 millimeters in Z from its current position. This variable is particularly helpful when I perform a single surface probe in Z. In fact, it's a permanent fixture in my Z-face probing routine. Again, these are two methods that I have successfully used to run the length offset calibration. Once completed, the offset is saved to the tool you specified in the program. In this example, you can see that I have saved the offset to tool number 9. Because I've already calibrated the length of my probe using the third method I mentioned earlier. Note that the lengths are not identical. The third method, and the one I trust the most, is to use my master tool to determine the Z coordinate of a surface. For this method, you will need to have a master tool and know its length. Here's a brief demonstration of how I do it.
Alright, this is probably going to be impossible to film and do at the same time. But what I'm going to do is I'm going to use this pin, right? And I'm going to adjust this up in Z. You don't want to go down, you want to adjust up. So I'm going to go up in Z, right, a couple, and then test it. And I'm going to go up in Z and test it. And at the point where I can, whoops, slide this pin under. Okay, I can slide it down. Now I'm going to go down one. Down. To where I can't move it under. Then I'm going to go down in my step. And I'm going to repeat the same process. I'm going to go up in Z, slide it, up, and when it slides, then I'll go down one, and then I'll go down to micron mode. And I'm working my way down to where this just goes under in the smallest resolution, okay? And then this is a known number, 6.35 millimeters, right? I can subtract that or do the math, and I'll have an accurate measurement in Z to compare with the figure we got with the probe.
Once you have that Z value, you can adjust your probe's length offset until it repeatedly measures the same value.
We ran the Pioneer probes. We ran the Pioneer length calibration to get the length of the probe, and it spat out 171.652. I know from previous calibrations that's grossly off. I'm usually in the 160s. But I can verify my master tool length. That's a physical length that I can check this against. So what I've done is I did a G54 single surface Z, and this is what it gave me. All right, with that tool offset of the probe. Okay, comparing that to the master tool, this is how much it was off by, 6.194 millimeters. So I adjusted to that. So I put in this as a new length offset for the probe, and as you can see, I continually did that to hone in. All right, so I put in the new offset, ran the probe again, and it was off by 0.3 millimeters. I had a new calculation, put in a new offset of decimal 145, and was off by 2 microns. Adjusted for that, was off by 1 micron. Now I'm chasing zeros. I adjusted for 1 micron, and all of a sudden I'm off by 7 microns in the other direction. I ran it again without adjustment. I'm off by 5. So I just flipped it right back to 145, and I was 0.
You're probably asking yourself now, how repeatable is the probe? To achieve accuracy and repeatability at the level called out in the manual requires perfection. Perfect runout, a perfect stylus with a perfect ruby, and a perfect surface on which to probe. I have none of these qualities in my shop, and I'm by no means perfect, quite the opposite. I work with crude metals at the best of times, and I haven't been able to adjust my runout to better than 5 to 7 microns. That said, I did some preliminary probing tests to see how accurate and repeatable my setup is. The first thing I noticed was that the first probe is usually the worst probe. These graphs show the change in values based on probe attempts. It not only shows that the repeatability of my probe is closer to 10 microns, but also that the first attempt is less accurate than subsequent attempts. Mind you, these are tiny numbers I'm talking about. Even with this level of accuracy, I'm confident using the probe to identify my WCS. The main reason I did these tests was to get a baseline prior to recalibrating my probe. I mainly wanted to see if the Y probing was compromised because some of my flip parts have been slightly off. You'll notice that in the Y web section, the delta of the first probing attempt was 0.007 millimeters off the baseline, though I don't think that is a big enough difference to cause notable problems when I machine both sides of a part. Interestingly, the remaining Y web probe attempts fell within the 2 micron range of repeatability. Now that I have the probe recalibrated, I think I'll rerun these same tests and compare. Let's hope it doesn't get worse. That concludes my video on how to calibrate the Pioneer OP510 probe. As ever, thanks for watching. Please let me know in the comments below if I got anything wrong or if there's a better way of doing something. That would be a great benefit to all of us. Cheers.